Well, great. Thanks for joining us, everyone. I know this is a different situation with everyone. I think most of our rep offices, a lot of you all are working remotely and we're working from your homes and trying to juggle work and everything. And so appreciate you taking the time to join us for the presentation. There are multiple Griswold on as well. So many of all know that I can't even really see who's on. So we all appreciate you taking time out of your day to join us. I am recording it so we can distribute it to anyone that missed the presentation so they can view it in their own time. Before we talk about the Griswold product overview and come into the actual products themselves, first I am going to just go ahead and mute everyone. It sounds like we still have people that are louder. Okay. So before we jump into talking about the actual product, we want to talk about hydronics and HVAC systems, and specifically the refrigeration, air conditioning industry. And I was telling someone in our presentation a few years ago that I had watched an A&E show, and it was counting down the top inventions in the 1900s. And my children were, of course, convinced that it was all of the technology and phones and how small the screens are and how small the phones are. And as they counted down, the top one that they identified as the most important life-changing invention was Mr. Carrier inventing air conditioning and refrigeration. And the reason they picked that as the number one is because in the early 1900s, when he designed that, it allowed for all the future technological advances to come because people could work in offices, they could be comfortable. And so it really shaped the world because it impacted productivity. And so honestly, at Griswold, we're all honored to work in that HVAC industry. Sometimes it's easier to hold in higher esteem other industries. And so we are honored to work in the HVAC industry because it does have a huge impact on the world. And I know you as our reps agree and feel the same way. So we want to talk about in general, HVAC and hydronics. So HVAC is the term used to describe heating, ventilating, and air conditioning. And within that, there is the hydronics that focuses on using water to cool or heat the buildings. And so U.S. Green Building Council, they've been studying buildings and specifically how energy is used in buildings. And they identified that one of the main problems is the wasted energy in HVAC systems. Specifically, they identified low delta T syndrome, and you can actually Google that, and it's such a high problem with so many building owners that there's millions of results if you Google low delta T syndrome. Partially it wastes energy because you're pumping excess water. It also leads to occupancy complaints. That's the other primary complaint of problems in the United States of America with building owners. They have the tenants complaining about hot and cold spots and flow noise. And so U.S. Green Building Council, we're a proud member of that council, really, in monitoring the energy. They identified that the HVAC system is a primary source of wasted energy. And you can look at it. They contracted with PNNL, Pacific Northwest National Laboratories, and they studied buildings across America. And the average energy expense in the buildings was about 35%. So this graph shows Baltimore. You can see you've got a different mix of heating versus cooling in Baltimore than you would in, say, Houston, where you'd have higher heating, less cooling. But in general, across the country, it's about 35% average. In the Pacific Northwest, Vancouver, Canada, that was the lowest part where it was about 24%. But almost every city and state, it comes in around 35. So that's a pretty large chunk of the energy expense in a building. And they identified one of the main issues is that the HVAC systems are rarely operating at their design efficiency, primarily, again, because of the low delta T syndrome. So we'll talk about the low delta T syndrome in another bit. So when you have the low delta T, the main reason that it's a problem is because your HVAC equipment is not performing at its optimal efficiency. And so what is the solution? Well, the solution is to absolute control, to control the delta T and control the flow. So if you can control your delta T and your flow, you can optimize the efficiency in your chillers and your boilers and your coils. And so when everything is optimized, then you reduce the amount of complaints that you have from tenants and from building owners. And so how do we control? Absolute control, it's in our tagline. How do we control that delta T? Well, if you look at this formula, which most of you that have been in Griswold presentations in the past have seen this, you've seen it in our literature. It's a very important formula that really just explains how the BTUs per hour, so that's the energy, the heat, the energy that is being used in these systems, the BTUs per hour is equal to the flow rate times the delta T times the constant. So in most cases, you're measuring the delta T, so that would be the temperature difference across some heating or cooling device. So all heating or cooling devices are either adding in heat or adding in cooling, and so you would measure how much BTUs per hour based on what that temperature drop is. And so you can see, looking at this formula, that the biggest way to control the delta T is to control your flow rate. If you look at the first row, you can see that we have a 2-degree delta T. And in the 2-degree delta T, to do that for 500,000 BTUs per hour, we need 500 gallons per minute. So we need a lot of water to make that 500,000 BTUs per hour. If we change the delta T to 5 degrees, then we only need 200 gallons per minute. And so you can see, looking at this, if we want a 20-degree delta T, which is the holy grail, that's where everyone wants to be, then you only need 50 gallons per minute. So you can see why controlling your delta T, controlling your flow, has a great impact on the BTUs that you're generating of heating or cooling, but it also greatly impacts how much water you're pumping, how much water you're heating up, how much water you're cooling down. And the way I like to remember this principle is, if you think about a hose in the sun, and so a hose in the sun that has a lot of water going through it, the water coming out the other end is going to be the same temperature as it was going in. You'll have a very low delta T. If you slow down that water to a very small trickle, so it's a very small flow rate, now you've had more time in that hose for the heat from the sun to heat up that water, and so you'll have a bigger delta T. So you can see the relation between the flow rate and the delta T just by thinking about the sun, and this directly impacts everything that we do at Griswold Controls, because at Griswold we're about controlling the flow. So to control the delta T, we need to control the flow. So how do we control the flow? And again, I know some of you that have participated in this are probably bored with these formulas, but this is another formula that is used throughout our industry, that is the flow rate equals the area times the pressure drop. You might be used to seeing it as the flow rate equals the CV times the pressure drop. And the CV is really just a function of how big that area is. It's something we measure in the lab. Everything has a CV. Our hoses have a CV. Our isolator S plain strainer has a CV. And so you can calculate what the pressure drop is if you know the flow and you know the CV. And so you can see in this equation, how do we change the flow? Well, there's two ways to change the flow. You can either change the flow by changing the area, or you can change the flow by changing the pressure differential. Those are the only two ways. You could also change the flow, I guess, by changing both at the same time. But there's really only two variables that come into play for how to change the flow. And so really that brings us to Griswold Controls. Jumping right into our product, this table represents all the different ways that Griswold Controls valves control the flow in the hydronic system. So we've got, each row is a separate valve category, and they use that flow formula that we just looked at. Flow equals the open area times the square root of the delta P. Each of these rows uses that formula differently to control the flow rate. And so we're going to go through all of these different product categories at Griswold to really talk about how each of those valve categories works in the HVAC system. The other important thing to look at in this table is the second column, obviously, is Griswold Controls, and there's the products that we participate in. And the other interesting thing is you look at this table and you can see that most balance valve manufacturers make valves for the balancing side, whereas actuated valve manufacturers, they make valves for the actuated side. So we've really, at Griswold, we span two different markets, two different areas of our industry, because we design and manufacture products in all of those categories. So the first category we want to talk about is automatic flow limiting valves. ASHRAE likes that term, automatic flow limiting. When David Griswold was designing our product, he called them automatic balancing. So you see that term used throughout the industry as well. But why is system balancing important? Why do we need to do balancing? And next week, we're going to really dig into why balancing is important. So this is a very small 2-minute section of the bigger presentation for next week. But a balance system in waterside terms is one where the terminal unit or the coil have the right flow rate at the right time all the time. And so basically the units close to the pump have the flow they're supposed to have, and the units far from the pump have the flow they're supposed to have. What happens in a system that's not balanced is you've got two situations. You've got either low flow or you've got high flow. So low flow can lead to hot and cold spots. If it's heating or cooling, it could be, if it's low flow and you want to be warmer, now you've got a cold spot and it's not warm enough, vice versa. If it's a situation where you want cooling and now it's hot because you don't have enough flow. You can have short circuiting and equipment malfunctions. You see this on heat pumps where they don't get enough flow right away, they will shut down. You get, in general, tenant dissatisfaction, where your tenants are not happy because, again, these hot and cold spots, and then obviously that leads to increased number of callbacks. So having low flow is not ideal. It's a situation, and I like to think about it. I don't have a hydronic system in my house. My house isn't huge, but the room that's really close to the furnace gets nice and warm, and the room farthest away in the house doesn't get warm enough, and it's always cold. And so if you think about your house, you probably have rooms like that as well. And so if you expand that to the bigger multi-floor, multi-story building, you can see that it would be a much more extreme situation. So on the low flow problems, that's one set of issues. The high flow problems have their own situation. High flow leads to erosion. It can be in the copper and the elbows. Generally, where there's more turbulence, there'll be erosion. And so if you've got more flow, you have more risk of that. Obviously, it leads to wasted energy because you're heating up and cooling more water than you need. It can lead to latent load issues, which is more of an issue when you're trying to remove the humidity from the air through your air conditioning cycle. And so if you have the flow is too high, then you don't remove that humidity. You can have equipment malfunction when you've got too much flow, and then obviously increased number of callbacks as well. So both of those, high flow and low flow problems, were issues that David Griswold wanted to take on when he designed this cartridge. He knew that in the building you had pressure changing, you had pressure differentials that were different, and then he, like I said, next week we'll go into balancing more, but he knew how water moves in pipes and where the water goes and how the ones farthest away don't get enough of that water. So he designed the original stainless steel cartridge. And this graph shows the pressure differentials on the x-axis, the flow rates on the y-axis. And this graph shows as the pressure differential increases, what happens to the flow rate. And it's the same equation that we looked at earlier. As the area changes, as the pressure changes, the flow changes. So for a constant area, as the pressure increases, you're going to have a flow increase. So that's the same thing here. As the pressure increases on the x-axis, your flow rate would increase normally. But with the Griswold cartridge, this cup on the top right side, you can see the little holes and the slots in that cup. And so the water goes into those holes. So if you think of it, those holes reflect some CV. They reflect an open area. And so we know that as the pressure increases, we should have more flow. But what happens is that cup presses on the spring. And normally you don't see the spring. This is just a cutaway image. So it'd be, fully contained. And so that cup presses on the spring. And as it does, that cup goes down, and those open area holes in the cup are now getting smaller and smaller. So as the pressure is increasing, we're decreasing the area so that our flow rate stays the same. And so that's what this horizontal line is right here. Sorry, I'm a horrible drawer on my computer, but that's what that horizontal line is. Basically, as that cup is moving and changing the area as the pressure increases, the flow remains the same. Below the pressure differential start point, it's just a fixed orifice. So it'd be like any of your actuated valves, any manual valve, where as the pressure increases, your flow increases. So if you're used to looking at our literature and the automatic flow limiting cartridges, you probably would recognize the 2 would be right here, and the 32 would be right here. So anywhere between 2 and 32 pounds differential, you're going to be a constant flow rate. And so that's why you've got that horizontal line. So that's the original, let me erase the drawing. That is the original design that David Griswold came up with in 1960. And a little fun fact is he designed the first balancing valve on the market in 1960. Oftentimes people think manual valves preceded, and we'll talk about manual valves later. But the first B&G circuit setter was launched in 1968. And so you can see that actually automatic flow limiting precedes even the manual balance valve style product that's on the market. So David's original design of this very simple cartridge was revolutionary back then, because as the pressure changes in the building, as someone opens or closes their valves or changes the pressure in one zone and impacts the other, you get a constant flow rate. It also made it so that the valves that were closest to the pump absorbed the pressure. They had that extra pressure, but they still remained at the constant flow, so they didn't have overflow. And that meant that the valves that were farthest from the pump had enough flow. So the cartridge was really 2 purposes. It balanced it in that everything had what it needed, right? The right flow at the right time all the time. And then as the pressures changed later, as actuated valves open and close, it maintained that correct flow rate all the time. So that's David Griswold's original design, and it's very similar to how it is today. The ports are all cut now on a laser. It's all stainless steel construction, so it resists corrosion. It's a very robust material. We have people every once in a while send us back old cartridges that look almost as good as new. We posted some photos on our Facebook of some almost 30-year-old valves that the cartridges looked almost new. So that stainless steel design is very resistant to corrosion and erosion and damages. The other key part about the cartridge, if you look at the top, I pointed out the holes, but there's also these parabolic shaped curves. And the purpose of that was to really resist noise and water hammer. So you turn off your faucet in your kitchen or bathroom too fast, you hear that clank and bang, and then it shuts off. So that's called water hammer. And so David designed this parabolic shape so that it's a very smooth change in flow. As the area is changing and the pressure is changing, there's a very smooth change in flow. And then obviously the stainless steel spring, same material as the stainless steel cartridges. So within our cartridges, we have 5 different sizes. The flow rates within plus or minus 5%. And we have multiple housings. So in the photo or in the images, we've got the isolator R in the top right side and the K valve in the bottom right side. So those are both brass housings. The isolator R includes the union and includes isolation. The K valve is just a flow limiting, and then the PTs upstream the pressure. So those are just two of the housings that we offer. And so we have multiple housings with multiple features. Many of our brass housings have the isolator series ball valves that have the repairable stems. You don't have to remove the valve. Some of the housings are combination style to reduce the footprint size. But it's really the same cartridge going into all of these different housings. And I just listed some of them. Isolator R, K-valve, isolator Y, threaded mini, threaded flange, wafer, grouped in, copper sweat. These are just some of them. You can go to the custom housing section. Our website, as well as Quick Quote, are all divided up into these same categories that we have in this presentation: automatic, manual, coil piping. So you would be able to see any of them on the website or in Quick Quote just by going to the category. And then in Quick Quote, you actually get to see the housing with a little image, so you can decide, you know, what extra complementary features do you want to add to your housing. So this is just a list of the most common valves that we see in the automatic flow limiting side. So the next category we want to talk about are manual balance valves. Manual balance valves are exactly what the name says. They are a way to manually, so by manual, that means some human has to set the valve to the flow rate. The automatic flow limiting, it arrives from the factory at the flow rate that the engineer has picked for the coil or the terminal unit or the air handling unit. So the flow rate is picked by someone, and our valve is shipped to match the equipment that it's going on. For a manual valve, someone has to manually set it. So to do that with any manual valve, you need some way to measure the flow, and you need some way to set the flow. And so for Griswold, we have the quick set and the quick disc valve, and they include a venturi. So if you look at the images on the right, the larger valve is on the bottom, which shows really a good cutaway of the venturi that really gives a, you can see how the venturi, the throat of the venturi is small, and then the before and after of the venturi. And a venturi is really the most accurate way to measure the flow. We did an application tip, I think in January, that why venturis are the best, it's called. And so we talk about how venturis are really, in the industry, everyone acknowledges that the venturi is the most accurate way to control the flow. The other ways that you can is, say, an orifice plate or a pitot tube. So we have competitors that can measure the flow through one of those means, whether it's the pitot tube in the large product or orifice plate in many of the competitors' products. But engineers and the industry all agree that a venturi is the most efficient way to, most accurate way to measure the flow. And basically, you're measuring the pressure differential from the throat of the venturi to the upstream of the venturi. And by doing that, you're getting an amplified pressure reading so that you can really fine-tune what the pressure reading is to get what the flow rate is. So all of our quick sets have a venturi inside. They also need some way to set the valve. So anyone's manual valve, you have to have some way of measuring and some way of setting it. So for our valves, in the 1/2 inch to 2 inch side, we offer the quick set, which has a ball that you use to set the valve. The quick disc has a ceramic disc to set the valve. And then our larger 2.5 inch to 20 inch venturis, quick sets, you use a butterfly valve. So you need some way in the field to set the valve to the flow rate that you want. And then with that, all the smaller valves have some kind of memory stop so you can set it. And for our quick set, we offer 1/2 inch up to 20 inch. And one of the main benefits of the venturi that we have designed is that you can install it at elbows, T's, or valves. You don't need any straight pipe length. And that is very rare. There's no one else in the industry that makes a manual valve that can be installed at an elbow or a valve or a T. Everyone else recommends either 6 times the pipe diameter or 8 times the pipe diameter upstream of the valve. Our Venturi design, we do not require that. So we are the only manual valve in the market that doesn't have any kind of piping limitations for where the valve can be piped. So when you're setting a manual valve, there's two ways to do it. You can look at a chart, or you can look at some kind of calculator tool. And what the balancer is doing is they're going to put their pressure probes into the PTs on the QuickSet or the metering stations, and they're going to measure the pressure differential across that valve, and they're going to go to the graph or the calculator. So in this, the calculator, I've set it at 1. And for the CV, they have a CV of 1.1. And so they would look at this and say, okay, the expected signal, the pressure drop I need to read across my gauge is 52.6 inches. So if they're higher than that, then they're going to close the ball. If they're lower than that, they're going to open it. So they're going to modulate, or move the ball or the butterfly position until they get the pressure drop that they need for that flow rate. And so NEB and ASHRAE and AABC, they all recommend that a manual balance valve have 3 passes where they're measuring it, setting it, and then going to the next one. And so it takes 3 passes because the first time you do it, you set it to say 52.6 inches. And then you go down the ladder and you move to the next one. And when you get to that next one, now you change the ball or the butterfly, and you have just changed your system pressure. So in changing your system pressure, now you've changed what the flow rate is in that first valve. And so you can guess, as you make it your way through the whole building, by the time you're at the last valve, that first valve is going to have a different flow rate than it did when you first set it. So then you're going to do the process again and do it for the whole building, and then a third time. And that's what's recommended by NEB and AABC and ASHRAE to really set the valve, to set that 3-way valve. I'm sorry, to set the manual valve 3 times. So we want to take that into account when we're talking about manual valves. We want to take into account that labor. And so this is a quick cost comparison of a K valve and a QuickSet. And it's accepted in the market. Nobody would argue if you said a manual valve costs less than an automatic valve. I mean, just by design, our manual valve is a Venturi, our automatic is the stainless steel spring cup housing. Just by the nature of the actual physical materials going into it, across the board, every manufacturer, the manual valve is going to cost less. It's a simpler product. There's no moving parts until the human moves it. So this cost comparison is for us, but it would also work for anyone in any manufacturer. The balancing labor, we put in a generous $50 per hour. I know some territories it's 3 times that, but half hour each one, because it's not just measuring the pressure drop, but you have to actually dial in almost the flow. So you've got to move that butterfly and then, oops, I went too far, go back. It takes a little bit of time to go up and down the ladder, put the probes in, and then dial in what the flow rate is. So balancing at half hour per valve, $50 per hour is about $25. Whereas the automatic, it comes already at its flow rate. And so we like to point out as often as we can that manual versus automatic, if you're talking the initial cost, yes, manual comes out ahead. But once you take into account the labor, you're really not saving much at all if you're doing manual. And then after the money is spent, the main question is your system in balance? Well, for the manual one, I put a question mark because I want to give credit to the manual balancer who, in the moment when they finished, it was actually balanced. Now, as soon as someone opens up, turns their thermostat to hotter or colder, changes the building, then it's questionable whether it would be in balance. But an automatic is always. It's always the flow that the engineer picked for that coil or terminal unit. So then the second question, will it stay in balance? Definitely, it will not stay in balance. um, because, like we've been talking about, as the pressure changes, the flow is going to change. Can you change the flow? That is the biggest resistance we get from manual balance loyalists is, well, I can't change the flow. What if I need more flow? What if I need less flow? What if I need to change something? And so manual, it's very true. You can easily open it or close it more to change the flow. At Griswold, we really wanted to take on that one years ago. And so we have said, you know, in the first year, if you need to change the flow, we'll swap out a cartridge. We're very generous with that policy, and we'll swap out cartridges to help people out because we want them to be able to change the flow rate easily without having the downside that people say that an automatic, you're stuck forever. Let's see, I have one question. Does any other geographic area experience the balancing contractor changing the same amount, be it manual or automatic balancing, or charging the same amount? I'm not sure if others experience that. I do know that there are some territories where, like NEB would be, for example, mostly manual balance valves, but we have one rep that is very close to NEB and speaks of their branches and has a very good relationship. And so again, we want to respect and work with them. And so they are the ones that do flow verification, which really, if they're signing off that they verified the flow, they should put the PT probes in, make sure the pressure differential is, you know, within the range, and then sign off for the commissioning side of it. But I don't know if they charge a different amount for automatic versus manual. Definitely on the hourly side, it would be more hours. On the manual side, because we designed these Venturis, it became very clear that it would be good to offer what we call metering stations, just using our Venturi that then they can use to measure the flow across the Venturi to know what the flow rate is. So our metering stations, we sell almost as many of those as QuickSets because the Venturi, again, is plus or minus 1% accuracy, and it's very accurate. You can add in a transducer, and the transducer can then give you the flow rate on your smartphone app, or the transducer can give the flow rate to the building management system. So the Venturi itself and the metering stations, we see that as a growing market within the manual category because it uses the same Venturis. And then the next extension of that, of course, is our BTU measurement. Again, you can see this is the same Venturi metering station. The red valve right here is the same one that we've been talking about. And so we've got that Venturi measuring the flow, but we've added in some temperature sensors. And so you can now, because we know the flow and we know the temperature drop, we can go back to our equation that we've looked at, that the BTUs equals the flow times the delta T times 500. So we can see that we can use that formula to calculate what is the BTU being used in this pipe. And so this is the BTU meter. And building owners look at this because they want to monitor where the energy is going in different zones. Maybe it's a mall and they want to know which store is using the most heating or cooling. Maybe it's a campus and they want to know where their heating and cooling is being sent. So it's a real good way that more and more U.S. Green Building Council is requesting and requiring to get your LEED points and your LEED, you know, the gold, bronze, all those different levels. They're really pushing to measure and monitor things more, not just monitor your flow rate anymore, although that was what they started with, but now monitor your energy as it leaves your plant. Where is that energy? Where is that hot water and where's that cold water going? So that's our BTU meter. And it was really a natural extension of our manual valves and our Venturi product line. The next category I want to go to for Griswold is our actuated valve category. We'll come back to coil piping packages later. We want to look at our actuated valves. So on this screen, we've got the Unimizer on the bottom right and the Atomizer on the top left. And those are the two main valves in the actuated valve category. And so all of our actuated valves, we'll see if we look at some of the pressure independent, all of them have these main four features. So the first is our equal percentage port. The equal percentage port is that little tan triangle-shaped port in these balls. And so this ball is in a different state of rotation if you're looking at the image of the ball. And the reason we did this is, as we were designing the quickset valves, we had great changes in flow by changing a ball. And any of you that have been in the field and tried to rotate a ball valve, you know that you move the ball handle and you don't get any change in flow, and then all of a sudden you're at full flow and you're like 20% open. And so we wanted some way to slowly change the flow. And this, we go into this in much, much greater detail, not next week, but the week after in our actuated valve seminars. Why do we want that equal percentage flow? Why do we want to slow down the flow change in any kind of actuated valve? But the main downside to actuated valves in the past that were using balls was that they had that big change in flow. So this optimizer insert was one of our first patented parts put into these actuated valves. And it really does make it so that the valve can control the heating and the cooling water very accurately and very slowly so that you don't get big spikes and big jumps. And as we all know, it's an actuated valve, so there's an actuator moving it. So the actuator is on top moving that ball. The slower the flow responds to the open area changing, the better, because if it responds quickly and that valve keeps rotating, then that valve's going to over open or over close. You know, it'll keep going when it shouldn't. So with the actuator on there trying to really fine tune where the flow is as they're modulating, this optimizer insert is crucial for good control. The other patented item in our actuated valves is the low torque seals. So if you're looking at this atomizer cutaway, you can see we've got the ball right here, and then we've got a white seal and then a black O-ring. And that white seal is a Teflon seal, and behind it there is an O-ring, and that O-ring acts as like a pillow. And so if you've ever just gone out to your job site and you've picked up one of our isolator valves and you've tried to rotate the ball, you know how tight those balls can be. And the reason that they're as tight as they are is because we don't want any leak by. So it's a logical way to set up the ball and have it really close off firm. But obviously, if you've got an electric actuator on there, you don't want that kind of high torque. So that O-ring sits behind the Teflon seal on each side. You can't see it on this image because the brass is in the way, but it acts like a cushion. And what this means is, in the 1/2 inch and 3/4 inch size, it's about equal for competitors, about 30 to 35 inch-pounds torque required. So that means the actuator has to be able to turn 30 to 35 inch-pounds. In the 1 inch size, we're the only manufacturer that does not have to go up in size to the next actuator. All of our competitors have to go to a higher actuator, either 70 or 85, just depends on what brand they're using. And so at 1 inch, 1 1/4 inches, they have to go to the next size up actuator. What this means is that's a huge impact on the price. If you look at this Unimizer, I like to look at it as the brass valve is about 1/3 of the price and the actuator is about 2/3 of the price. And physically, it looks kind of that way too, so it's a good way to kind of remember. So if in the 1 inch 1/4 inch size, all the competitors have to go to the next size actuator, they're doubling that actuator price, and that's the bulk of the valve's price. So that can really impact if you're looking at a job and you've got all sizes of control valves, which most jobs have multiple sizes. It really impacts the price and the ability to be competitive. For Griswold, all the way up to 3 inch is 35 inch-pound actuator. Like I said, the competitors at 1 inch and at definitely 1.25 inches, everyone goes to the next size. Competitors also then at 1.5 inches and definitely 2 inch go to even higher. So they go to 120 or 133 inch-pounds. So they have really impacted the actuator price, which impacts the initial cost, but any building owner, any maintenance person, they're looking to replace. What is the replacement cost? Because if you're, again, looking at this valve, the first thing that will fail, the whole industry agrees, there's no debating this, the first thing that will fail is that actuator. So they're replacing actuators in 3 to 5 years. It's normal. No one, if it's 3 years and you have to replace the actuator, no one's going to really even bat an eye because it's very normal to have to change the actuator as it's rotating. So if you've got a high torque actuator on your valve, not only did you pay more for it when it was installed, but then in 5 years, you now have to pay that higher actuator price every 5 years as you replace that actuator. So that low torque seal really has a big impact. And as you go up in size to the 4 inch, 5 inch, and 6 inch, it's even greater. And some of you may have seen the color flyer we did about the 3-way Unimizer 4, 5, and 6 inch. When we did the analysis looking at competitors' pricing that they publish freely on their website of 3-way butterfly valves with actuators, our 3-way Unimizer was less than 50% your price to what you could buy a 3-way actuated butterfly from our competitors. So as you go up in size, this has even more impact on the 4 inch, 5 inch, and 6 inch, where we're a fraction of the size, the torque required. With that topic, we have our patented repairable stem. And this is important. I said no one expects an actuator, it's not a surprise if you have to replace it in 3 to 5 years. The actuator manufacturers, they try to say it's good for 10 years, which is about 60,000 cycles. But if you've got a system that's modulating constantly, you could hit that 60,000 cycles in 3 years, and it's not unheard of, and it's actually very common. Well, the second most common part to fail, if you're looking at the valve, would be then the actuated stem, which makes sense. It's rotating as much as the actuator is. And so that's why we've got our patented repairable stem. And we talked about that a little on the flow limiting, but we have a real good cutaway of it right here on the atomizer. And you can see we've got this Teflon seal at the bottom. We've got a grease reservoir right here. We've got a black EPDM O-ring, and then we've got another Teflon seat. So those 4 things go together to make up the repairable stem. And it's important because you've got 2 Teflon seats, an EPDM O-ring, and the grease reservoir is actually packed with grease so that it really protects that O-ring. If you need to repair this stem, you can remove it from the system without shutting down your system and removing the valve. You just have to release the pressure, usually in a drain or a PT, release the pressure, and then you can remove the yellow plate or the screw on the isolation handle, and you can remove the stem and replace the stem. Now, I'd say it's interesting because we launched that in 2007, and we sell very, very, very few, a handful a year of repairable, of stem kits to replace valves that were sold in 2007, 2008. So because it's such a robust design, that stem is not failing, and so you don't have to rebuild it. The one, you've got incredibly long life for the stem. We tested it up to 600,000 cycles, and it didn't leak at 600,000 cycles. So again, industry standard is 60,000, and we took it to 600. But then if there is a problem, if some chemical somehow managed to attack that O-ring or something happened, you could repair it. So worst case scenario, you could actually repair it. But again, we haven't really seen any inquiries for that. We do have the stem kits if anyone needs it. We sell more as spare items that people like to put on their shelf. And then the fourth really important thing on our Unimizer and Atomizer and our actuated valves is the universal mounting plate. And that's this black plate that you see right here on the Unimizer. This image shows a Siemens actuator. We did it universal because we don't want to tie ourselves to any one actuator brand. And so we're compatible with Johnson, Honeywell, Belimo, Siemens, Schneider Electric, KMC. We offer Siemens and we offer KMC. They're both really good actuator brands, and so we will offer that, but we also offer to take the actuators in and we'll assemble it. It's actually also very easy to put the actuator on yourself. Even I can do it, and if I can do it, anyone can do it, and it takes less than 30 seconds. So the universal plate, though, allows it so that you don't have to be brand loyal. If you want to be brand loyal, great. I guarantee ours fits with it, but you don't have to be brand loyal. So this is the basic actuated ball product, which would be the Unimizer and the Atomizer. The Atomizer on the left, you can see, combines the automatic flow limiting cartridge. The category that also uses the same actuated ball valve is pressure independent category. And so I want to talk a little bit about what's the difference between an actuated valve and the pressure independent valve. And so if you're looking at the graph at the top, we've got a traditional actuated valve, which means that some actuator is rotating that valve to some position below full open. So the full open would be this first top graph, this curve right there. Let's say the yellow would maybe be about 50%. And so you would have different curves that as the ball or the globe or whatever is rotated to, the valve would then sit on that curve and the flow would change as the pressure changed. And so that's what we've got in this graph is we've got multiple valve positions are shown by the different colors, and we could actually fill this like a rainbow with tons of lines because the actuator can, have so many little incremental fine movements, but this is just to really show the difference. And that actuated valve is going to then stop moving. And when it stops in its partial position, say that yellow line, as the valve is not moving, we use our same formula. The flow equals the area times the square root of the delta P. So the area is now fixed. If the pressure changes, now you can see we're going to ride this yellow line. So an actuated valve would then, because the pressure changed, someone did something somewhere else in the building, they wanted more heating, they wanted more cooling, they changed the pressure. So now if the pressure went up, now I'm going to get more flow on my yellow line. So I'll go from the lower point to a higher flow, or I'm going to have less flow. And what that means is now that zone doesn't have the flow that it needs, right? It was satisfied, it was good, it wasn't moving, but now it's got more flow or less flow. And so the thermostat or the building management system sends a signal and says, okay, rotate it again. So it's going to leave the yellow curve and it'll go, maybe it'll close it more to the lighter blue curve that's under it. So with an actuated valve, as the pressure changes, you're going to have flow change. You also, as the position changes, you'll have flow change. With a pressure independent valve, we only want to change the flow when there's a load change. So someone in the room has changed the load, whatever. Maybe they turned on more lights, turned on more computers, they need more cooling, they need more heating. Then we want the actuated valve to, yes, open. We need more cooling, so open the valve more. We don't want to have any flow changes because someone somewhere else in the building does something. If someone else does something, I don't care. I want my flow to stay the same. I don't want to have to keep cycling and rotating. So that's the purpose of the pressure independent valve, is it takes an actuated valve, it allows it to modulate to positions below full load, but then the flow rate doesn't change once the pressure changes. So again, as the valve stops modulating, it's no longer moving, and we want to remain constant flow. And if there's a pressure change in a traditional actuated valve, but in a pressure independent valve, it is exactly what its name implies. It's independent of pressure. The pressure can do whatever it wants, and the pressure independent valve will remain the same. So in the pressure independent category, we've got the PIG-V valve, which is this valve shown on the left side. The PIG-V valve has a space saver version and a standard version. The standard version has an additional isolation handle, but functionally they're very similar. They're 1/2 inch to 3-inch valves, brass housings, and there's a cartridge inside. And some of you are used to years and years of selling flow limiting where the cartridge is set for 5 GPM or 10 GPM. In the pressure independent valve, the cartridge actually doesn't set the flow. The actuated portion does. So in the PIG-V, the ball sets it. In our MVP valve, a plug sets it. And so as that flow is set, again, the loads change. The system tells it to open or close more to meet the load demands. Once that's set and that actuator is no longer moving, now if there's a pressure change, the cartridges in these valves and the diaphragms maintain the pressure drop across those flow elements. So it's a little bit different concept, but again, the point is the same. We want to remain constant flow even as the pressure is changing. And so we do it the same ways by modifying the area and holding the pressure constant across that area. And so the pressure independent valves, some have said that this graph here on the left reflects an infinite number of GPMs. Again, I can't put them all because the actuator, like it has 10 increments per point, per control point, and so hundreds of positions that you could have below full flow. And so the pressure independent valve is good for when you want to control the flow even at reduced load conditions. So you want to maintain plus or minus 5% even as the load conditions are changing elsewhere. You want to maintain the flow, but you want to change the flow rate to a different flow because the load conditions have changed. So as the load changes, you need to respond, change your flow. Once that flow's changed, then you maintain the constant flow rate by maintaining a constant pressure across the valve. Our PIG-V does have the field repairable stem as well as the low torque ball and the universal mount. You can see the universal mount here and the yellow plate showing the field repairable stem. The MVP valve is the larger valve that now goes up to 10-inch in size, and it's a flanged valve, and it's a very compact valve compared to the competitors' valves that are out there that are considerably heavier weight and much larger physical footprint. And then we have as well the Pinnacle valve, which is the newest pressure independent valve, and it is a zone type valve, so it's got the cost benefit of a zone valve, but it still gives you the pressure independent features. And so we'll talk about all of these in much greater detail in the actuated valve presentation in 2 weeks. The next category that Griswold entered after we launched our pressure independent valves is called temperature independent. And again, we go back to our basic formula that I know I always am talking about. But you look at this formula and you think, wow, wouldn't it be cool if I just controlled the delta T instead of controlling the delta T by controlling my flow? If I could directly control the delta T, then I can have that holy grail 20-degree delta T or even 25-degree delta T just by dialing it in. And so Griswold launched the EPIC system a couple years ago. We are excited that BACnet is coming, hopefully in the summer, late summer, early fall. That's been, I know, something that all of you reps have been asking about. And so you're familiar with this because we did go over the EPIC system when we launched it. But just to do a quick summary, it's the same pressure independent valve that you're used to seeing. So in this image, you can see the MVP valve, which is the pressure independent valve. So you've got an actuated control that will modulate to different reduced load positions. You've got the pressure independent feature so that if the flow rate, if the pressure changes, the flow rate doesn't change. So that means you don't have to rotate your actuator as much. But having the pressure independent valve built into the EPIC system is really key, and that's why EPIC actually has PI built into its name. With this, though, we have two temperature sensors, and the temperature sensors are key because, again, we're trying to control to the delta T. You know, this is the most important equation, and controlling the delta T is the most important thing. And again, U.S. Green Building Council, everyone comes back to this low delta T syndrome. So if low delta T is such an issue, why don't we just control the delta T? And to do that, you have to have sensors. And so in the EPIC system, there are two temperature sensors. There's also two pressure sensors so that we can know that the valve itself is within the pressure differential range. There's the ability to have a flow meter, and then obviously calculate the BTUs. And all of this is, because it's Bluetooth compatible, it's all visible on either the iPhone app, Android app, or on the building management system. And again, when we do have BACnet finally, that will make it that much easier to kind of plug and play, put all that data right into their building management system. And so the EPIC system, it's not just a way to, it's not just a pressure independent valve, it really is a way to be temperature independent because we're directly controlling the valve based on what delta T we want. So those are the main valve categories that Griswold participates in. Within those categories, there are numerous products, and like I said, the website and Quick Quote each have whole pages devoted to those, and you can see those valves. But within actually the valve categories, a lot of what we sell, almost 50%, is put into a package. And so I want to just go over a few of the last little categories that Griswold is very active in, and one of them is helping contractors build their packages. If you look here on the right, this is just a typical coil piping package. They always have isolation valves before and after the coil. Good ASHRAE recommends it. It's good practice. Strainers, obviously, to protect our cartridge, but we recommend a strainer because your coil needs a strainer, your control valve needs a strainer. Oftentimes that control valve will end up with a smaller port than our valve will have, and so that control valve really needs to be protected. It's recommended to have union to your control valve. Again, that's partly because the industry standard was to replace your actuator in 3 to 5 years, and then maybe even your valve if it was leaking in 3 to 5 years. With Griswold, that's not as much of an issue, but the industry kind of has accepted that you need to have your union pointing to your control valve so that you can easily drop out right here, the union tail pieces, so you can easily drop out your control valve if you have to change them. Also an air vent, that's very good practice, and ASHRAE recommends that, and obviously an actuated control valve, and then a balancing valve, whether it's automatic or manual. And so Griswold started making coil piping packages to help contractors put all of that together about 25 years ago, and it has become a big, big portion of our business. It makes it very easy for the contractor because they just have to install at 4 points. They don't have to install a bunch of components. It helps the contractors. They don't have any delays. They're trying to source all the different parts. It's just coming from one source. Contractors used to tell us that it saved them when they would do it themselves 2 to 3 times their labor because we're doing it in the factory. We're able to charge a very competitive rate. And then because they're shrink wrapped, it makes it very easy to distribute it at the job site. So our packages are actually very, very popular. And we will take anyone's control valve and mount it. Obviously, we would love if the Unimizer was the control valve of choice and everyone was putting that on their packages. But we know how the industry works on the actuated side, and people have quotas and people have rules. And so we'll take anyone's control valve and we'll mount it on our package just to make it very easy for the contractor. This is a service that we started out offering to contractors, and it really allowed us to incrementally build the business because now we're adding in all those complementary parts. Instead of just supplying an automatic flow limiting valve, we're now supplying the isolation, the strainers, the unions, the air vents. And so it makes it, and it's very easy for the contractor. The last category that we're going to talk about is the potable water valve. And we did a application tip last year about Griswold solving the cold water shower issue. You know, we talked about the issue, the unbalanced systems for hydronics are basically, it's unbalanced if you don't have the right amount of water that you need. And how, you know, in a building, you can have a lot of hot water close to the pump and not enough far away. Well, that same problem exists in a potable water application. And I was very entertained reading extensive research that people were doing on how to balance their potable water system, and they're using multiple pressure reducing valves and thermostatic valves in series and on branches and on the mains, and really doing a lot of different things to try to make it so that their potable water system is balanced. The goal is, again, the right amount of flow all the time. And you can imagine in a hot water potable system, the cold shower in the morning is going to lead to a lot of occupancy complaints if you run out of hot water on those units that are farthest from the pump. So our same stainless steel cartridge solves that same problem. So it's, again, it was very interesting to read all of the crazy scenarios people are doing to try to solve that using traditional products that's in the industry, when our stainless steel cartridge is like the perfect solution. So all of our potable water valves are certified to NSF 61G, also to California law, federal public law. And so we have within that category the K valve. That's the one that we started with in 2011. And it's the same K valve, but we offer the low lead version, and it's certified. We also offer the quick disc in 1/2 inch and 3/4. And then the Unimizer we offer in half, the two-way Unimizer in 1/2, 3/4, and 1 inch. And all of those valves are certified, our certifications on our website. And so any of those would work. But really, where are these valves being used? A lot of dormitories, condos, anything where you've got multiple users on the same hot water system, hotels. Nothing worse than being in a hotel and having a cold shower. It's beyond irritating. And I want to go lecture them about how they can just put in valves to make sure that everyone has the water they need. So anyway, that's the last main product category that we have at Griswold. And that really concludes what we wanted to talk about, which was basically all these different products that we have to control water. We're controlling water by changing the area, changing the pressure. All of this is just different ways of controlling the water in the hydronic system. And so that concludes this week's presentation. Next week, we're going to do more details on why is balancing required. I think everyone intuitively knows you just don't get enough hot water or cold water at the end, but we'll talk about why. And then in 2 weeks, the actuated valves. So appreciate so much all of you guys joining us today. I respect all of you for trying to stay current and learn everything you can during this time where everyone's kind of working differently. So everyone at Griswold, we really appreciate all of you as our reps. Really showing your interest in Griswold. We respect you a lot, and thank you for that. Have a great day, and I will distribute the recording later. And if you have any questions, feel free to call me or email me.